So in this tutorial I will state some propositions and prove it. It's related to that, means smooth morphisms, means fiber of means dimension of fiber actually of a morphism. So let me first state the proposition. Let X be a variety over some field K, algebraically closed of course, and let Y be V of F, which is the set of zeros of a regular function on X. Okay. Then for each point Y inside Y, capital Y, we have dimension of Y at Y. This is greater or equals to dimension of X at X minus 1. Means first recall the definition of this first recall that for X inside capital X, this dimension of X at X, this is defined as the maximum of R inside this natural number union 0, say positive non-negative integers, such that, means this singleton X, this is X naught, this is strictly contained in X1, this is strictly contained in up to XR. This is a chain of irreducible closed subsets of X. So this is a definition of this dimension of X at small x, at the point small x. Now it can be easily, one can see that this is nothing but dimension of the local ring OX X at X, the local ring at small x. Okay. So and when X is irreducible, then these two definition coincides, means dimension of X at this is equals to dimension of X. These two definition coincides. Okay. Now we come to the proof of the proposition. It states that if Y is the zero set of a regular function on X, then its dimension can it's greater or equals to dimension of X minus 1. Means at this point, here this is actually equals to Y, because Y is inside, small y is inside Y, so it is also inside X also. Okay. So now proof of the proposition without loss of generality. Assume that we assume that X and Y, here we are considering X and Y, means X as a variety, so we are always considering this is irreducible. Okay, means in our definition of variety we are considering irreducible. We can also do it without the irreducibility, means still the proposition holds, but we are considering this X as an irreducible variety. So we assume that X and Y are affine we can, okay, we assume, without loss of generality, we assume that y is x is affine and y is uh, irreducible and affine, irreducible and affine. Means y as a affine subvariety, we can means say, okay, or is a, and y is a, is an affine subvariety. Variety of x. It means this is irreducible also. Now why? For that you need to check. You need to consider the affine open coverts and then you have to reduce it to this case. Okay, check. Okay, now Noether normalization lemma, Noether normalization lemma, this states that this states that that there exists some polynomial algebra, polynomial ring, means k x1 up to xn in n variables, such that this is sitting inside and we have some injective map. Okay, yes. So we have the means we here we assume that this is affine, so we are considering the coordinate ring ax. So this will be this is a finitely generated this ax, yes. So this is a finitely generated k algebra, right? Now, so this is integral, this extension, this is a means we can find a polynomial algebra, means polynomial algebra k x1 up to xn in n variables, such that this is integral. Okay, and where x is nothing but this n is nothing but a dimension, sorry, okay, anyway this is integral. So integral means it's their dimensions are same, so dimension of this ax, this is equals to dimension of k x1 up to xn, which is nothing but equals to n. Now from here, from this statement, it shows that means we can means it implies that we have a morphism from x to an. This is a finite morphism and this is surjective also. This is finite surjective morphism. Okay, so this is what Noether normalization lemma implies. Okay, and n is the dimension of, and this is equals to nothing but and dimension of x, which is equals to dimension of ax. We already know this is the case for affine variety, so this is equals to n. Okay, now from here also we have y to be some y to be some zero set of some regular function for some f inside oxx. This is equals to another, means this is the regular function and this is nothing but this is isomorphic to ax. Okay, now consider the map. Now consider this morphism phi, which is nothing but pi comma f, this pair where x goes to an cross a1, small x goes to, first it goes to pi of x, and here this goes to f of x. Okay. Now okay, now because this now we have this field, this is inside this field of rational functions on x. Okay, so this is nothing but a of x is the integral domain, so k of x will be the, means it is the quotient ring, quotient sorry, field of fractions of of x. So this is algebraic, this extension is algebraic extension. So and f is also inside k of x, right? So then there exists a, means then f satisfies a minimal polynomial with coefficients from this field k x1 up to xn, this. Okay, let this p t, this polynomial, this monic polynomial up to am be the minimal polynomial of f over k x1 up to xn. So we assume this is the minimal polynomial. Okay, now claim is that this all this each ai, this is actually belongs to this polynomial ring k x1 up to xn. Okay, so for that let q t be a monic polynomial, with coefficients from k x1 up to xn such that q of f this is equals to 0, right? Because f is means we know that here we know that this ax is integral over this k x1 up to xn, this polynomial ring. So from here, and f is inside ax, so we can say that so f is integral over this k x1 up to xn, this polynomial ring. So there must have a monic polynomial with coefficients from this this polynomial ring such that q of f equals to 0. So it says that, so this is a means equation of integral equation. Okay, so this implies that from the means, because pt is the minimal polynomial, so this implies that this pt divides qt, right, q of t. So this says that all the roots of p of t, this satisfies the satisfy the equation q of t equals to 0, this equation. So it means that all the roots of p of t are integral over this polynomial ring k x1 up to xn. So this means that from here it implies that means we get that each ai this is equals to, and this is inside this k xn up to xn. Okay, because these coefficients can be, means we can write these coefficients as means some symmetric polynomial as means some symmetric polynomial expression of this of the roots of the polynomial. Okay, so from there actually it implies that each ai is inside here, inside this polynomial ring. So now consider this p of t as a polynomial inside this polynomial ring k x1 up to xn comma t. This polynomial means in n plus 1 variables, means consider this polynomial, this p of t. Okay, now let z to be the zero set of this polynomial, means when we are considering it as polynomial in n plus 1 variables. So it will be inside an cross a1. Okay, now clearly phi of x, this is inside z, so this is check. Okay, clearly this is true, and our claim is that this is not only just this phi of x image is not inside just z, this is actually equals to z. This is our claim, and for this claim I am not going to do it, but it follows from the fact that yeah, first you have to show that, number one, you have to show that this phi of z, phi of x, this closure, this is equals to z. Okay, first show that, number one, and the next, it follows from the fact that means finite morphisms okay, first show that, show this. Okay, now finite morphisms are closed, finite morphisms are closed. So this phi of x is not just inside z, this is actually equals to z. Now this I leave as an exercise, that this phi of x, this is actually equals to z. Okay, so please try to do it, and means if we can use this fact, then it will imply that look, so this y is actually nothing but v of f, right, inside x. So this is equals to, if you means see the means how we defined this phi, this is phi inverse of this t equals to 0, this hypersurface intersection image of phi. Yeah, what is the phi? The phi is this x to an cross a1. So x goes to pi of x comma f of x, right. So if we intersect this with the means t equals to 0, this means this we can think as what, this O of an cross a1, this we can think of, this is isomorphic to k x1 up to xn comma t. So in this way, means we are saying that this t equals to 0, this hypersurface, we are considering this is means we are intersecting with this image of phi. Then if we means take its inverse image, then it is actually y, right. So now this says that y equals to phi inverse of this intersection with this hypersurface intersection. Now this image of phi, this is equal to z, and z is nothing but zero set of this this P of t, means this is defined by this P of t equals to 0, this equation. Okay, so this is equals to now P of t, actually we have means written this P of t as this t to the power m plus a1 t to the power m minus 1 up to plus mn am. Now so the common zero set will be nothing but this am equals to 0, this hypersurface means this equation, this means yeah, this intersection will be given by this equation am equals to 0. Now am equals to 0, this is means am, this is a polynomial inside kx1 up to xn, so in n variable. Okay, so it means that dimension of y, this is greater or equals to dimension of this am, this is equals to 0. Okay, so now this is equals to n minus 1, right? So this is a simple means affine dimension means dimension theorem. Okay, so now this is equals to means we know that n is equals to dimension of x, so this is done. So this is the case, means here we are considering irreducible means varieties we are considering they are irreducible. So these definitions actually coincide, this dimension of x at point x, this equals to dimension of x, because these are irreducible, so this coincides. So from using this we can show that we are done this proposition. Now from this proposition I will make a remark. Now if y is a means it defined as the zero set of some say L number of regular functions for some regular functions on x, then means x and means x is a variety. Okay, then this dimension dimension of y at y, this will be greater or equals to dimension of x at y minus L. You have to use the repeatedly you have to use this previous proposition, then you get this, means here we use for only v of f for only one regular function, here we are considering L number of regular functions. So for each regular functions we can means show that use induction for this proof, use induction. Okay, now the means main proposition that I want to means prove, proposition let f from x to y be a dominant morphism. Dominant morphism, I don't know if dominant morphism is needed, I don't think it's needed. Okay, so still means means we mostly consider, means we mostly use this means in this case only, dominant morphism case only of varieties, we are considering varieties to be irreducible. Okay, then the dimension of the fiber, this dimension of then for each x inside capital X, dimension of this f inverse of fx, this fiber at x, this is greater or equal to dimension of x minus dimension of y. Okay, so for proving this we will use now this previous proposition. Now proof, without loss of generality, assume y is affine. Okay, now let y means phi to be y to an with finite surjective map. This is means from Noether normalization. Noether normalization lemma from. Okay, so we have this where the dimension of x, dimension of y, this is equals to n, right? Now we have this map, so x goes to y, y to an, we have this map. Now here this is finite surjective, this is our pi, and this is our dominant map. So here x goes to some fx, and this fx goes to some point inside this an, some point. Okay, now from here we can see that f inverse of fx to okay, now this point, this is this is a point inside an, so this is defined as a means common zero set of n polynomials. This is can be written as some, say this point, say we name it like a1 up to say an, so or alpha 1 up to alpha n. Okay, so this is actually nothing but common zero of this xi minus alpha I, common zero of this this collection I from 1 to n. Okay, this collection, right? Now if we pull means now regular functions goes to regular functions, right? So means from k x1 up to xn to ox, yeah, we have a map because x to y and y to an, we have this map. So we are it induces a map of this k algebras, right? Now xi minus alpha I, they goes to say inside fi, they goes to fi. So from here it says that this f inverse of f of x, this is actually zero set of these polynomials, these regular functions fn. Okay, so now dimension of, what will be the dimension of f inverse of fx? This will be greater or equals to dimension of this is inside x, we are considering inside x, this will be dimension of x minus n. So and n is nothing but dimension of y, so this is dimension of x minus dimension of y. So this is means here we didn't means we didn't need this the dominant, so in these conditions we don't need it. Okay, so okay, so we are done. Okay, let me stop here. Thank you.